Okay, this is the lecture that's meant to kind of summarize the ideas from our lecture on DNA. Here's the breakdown. You have biological parents. They pass on stuff to you. They pass on 23 chromosomes each. You have these 23 pairs. These pairs, zoomed in, look nothing like my cartoon, but it's a pretty good cartoon all the same. This is a spiral of DNA wound around a molecule, of which I don't remember. Maybe some of you do if you're in biology. You get one from your dad, one from your mom, and there are stretches of this DNA that are genes, and then there's stuff in between the genes. At certain locations between these genes, we've identified repeating sequences of words. So you imagine this piece of the chromosome zoomed in as this spiral of DNA, unwound as this double helix structure. And sometimes you find repeating patterns, TCTA, 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 TCTA. And different people have a different number of these patterns. You know, your dad might have had 10 of them, and your mom might have had 13 of them. So then at this location, say, this is the name of an actual location. I don't know which chromosome it's on, but it's on one of the chromosomes. This is the pattern at this location. So at D2S44, there's a pattern, TCTA, that they have figured out the various frequencies of occurrences in various populations, Caucasians, African Americans, Hispanics, whatever. And those identify you. If you have a 1013, then other people might have 1013s too, of course, but they're not likely to match you at all 13 of these loci. So there are 13 locations on 12 chromosomes, and this piece of information, let me go down here, are these two numbers. So this is the ID at this locus. It's a pair of numbers indicating the two alleles. The alleles are these varying numbers of repeats. All right. So you have to figure out how frequently a 10 occurs or a 13 occurs, so that then you can figure out how frequently a 10 and a 13 occur. That's Punnett square stuff. We're not going to do that, but I'd like to explain how it works. So let's move on. You saw in class that the allele frequency for different STR for different alleles at different loci are huge tables of numbers. So this is important. This is a number we're using. Whoops, I'm sorry. We're going to say that the odds that two people have the same allele at the same locus is 7.5%. It's an average. Sometimes it's more, sometimes it's less. So this allows us to do some rough calculations. There are 13 loci that are used, technically 20 now, but we'll go with 13, on 12 chromosomes. We assume that the STR lengths are independent. That is, if you had 10 repeats of this phrase, it shouldn't predict anything about another allele on some other locus. So if you have 10 here, it shouldn't say anything whatsoever about whatever repeating phrase is found on this chromosome. So the probabilities of finding a certain set of numbers here should be independent of the probabilities of finding some other set of numbers here. That's the assumption, which is backed by some population genetics. So what are the odds that two people have matching alleles at all 13 loci? Well, it would be this number. You'd multiply the probability by of one match times itself 13 times. Kind of like flipping a coin. What are the odds of getting heads 13 times? Well, it's half times a half times a half times a half, or whatever. So this is it, right? This is kind of a hard number to understand. So here's an attempt. This minus 15 means move the decimal point over 15 times. And then you can go through. You can always identify, tens, hundreds, thousands, 10,000s, 100,000s. Identify these milestones and work your way across. Here we're at the 2 is at the 1,000 trillionths spot. So 2.3 over 1,000 trillion, or about 1 over 500 trillion. Wow, that's an extraordinarily small number. It's extraordinarily unlikely, okay? It would seem. Okay. And this, be careful, this is the probability that someone would match, say, my DNA, right? So if we took my DNA, right, and you were to match it to every other person on the planet, the odds that you would find one is pretty small. It's not zero. And you could find one. Just because something is incredibly rare doesn't mean it can't happen. And certainly if you do a pairwise comparison, I never thought of this actually. How many pairs can you make with 7 billion people? Temporarily nerd sniped here. So there's 7 billion. Here's 7 billion and 1. That's kind of silly. Doesn't make a difference at all. Divided by 2. So yeah, so if you were to look at all possible people, there's more than enough people to find a match. But that's different than the question of, will it match you? Right? Will it match you? Now, I showed this next chain in class today. This is an inference chain. And here's how it works. So suppose there's been a crime. They find DNA at the scene. And I'm the suspect. And they test it against me. So they report a match. That is, whatever the laboratory where they do DNA reports a match, their various graphs or whatever, with mine. Well, that doesn't mean it's a true match. As we've already seen, one of the videos talks about bias, and we know they can make errors just due to handling or contamination at the lab. It's possible, it's not true. So even if they report a match, it may not be true. But let's suppose it is a true match. Then it doesn't mean I'm the source. It could be a coincidence or a relative. This is unlikely, but it's possible. You have to rule this out definitively. To rule out that any of my relatives did it. Okay? And then, if it's been established that I'm the source, it doesn't mean that I was actually present at the crime location or when the crime happened. Evidence could have been accidentally trampled in or planted. There was a case, there was a rape case where there had been consensual sex earlier in the day. And then there was a rape later in the afternoon. There's some mess up of genetic material. Maybe that wasn't it. Maybe there was a convicted rapist who had claimed that he had had consensual sex. That's what it was. So there was a rape, and of course there was DNA found, but the suspect claimed that he had had consensual sex. He was explaining the source of material. He claimed that somebody else had raped her later on. True or false, whatever, you have to establish that that DNA is there because something was done to get all the way over here. And remember, the job of the defense is to take a big old pair of scissors here. Defense. Man, I wish I could cartoon here. And snip any one of these lines. Meanwhile, the prosecution is trying to establish these lines. The prosecution wants to go from here to here to here to here, and at least use this evidence to imply guilt. Right. You saw today in class, in fact, I gave you an example. And in each section, somebody correctly pointed out that you have to be careful of the verbiage, not to confuse this match probability with source probability. Moving right along. So, in the John Puckett case, there was a rape and murder in the 70s that was a cold case, and one of the articles talks about this, so hopefully you're familiar with it. And we did a class session on it. And he was found by trawling through a database. They took this evidence. It was 5.5 Loki, So not a complete profile by modern standards. But the odds of a match are still pretty slim. If you take 0.075 raised to the 5.5, this is right. So like 1 in a million, 1 in 10 million. So not super likely. The defense argued that the probabilities that had been used were grossly overstated because there had been a lot of matches. Where was it? I wrote it somewhere. Oh yeah, jump ahead a little bit. Right? So in 2001, an Arizona DNA database of 65,000 profiles, they had found lots of matching pairs at 9 loci, which is a more stringent requirement than the 5.5 of John Puckett. So what's going on here? Well, this is where we review the birthday problem. And this is pretty tricky because we're talking about 2 probabilities and also our personal experiences. If I ask a bunch of people, is your birthday my birthday? And they say no, I'm not shocked. If somebody says yes, I feel kind of special. I'm like, no kidding, that's amazing. However, even though we know now from class that if you have a group of 23 people, it's very likely that somebody has a matching birthday. That person is going to experience the rarity. They're going to experience the unlikelihood that somebody actually has their birthday, even though we know that somebody has to have that experience. It's a little like, winning the lottery. That person that has the winning lottery ticket feels amazing, right? They won all kinds of money. But you very seldom assume that a lottery winner cheats, even though the odds of winning are usually, 1 to tens of millions, something like 1 to 10 to the 7 or even more. It's exceedingly unlikely that you're going to win the lottery, yet somebody does. We don't find it very surprising when somebody does. We would find it very surprising if we did. This is understandably very tricky, and you've got to reconcile these 2 things. It has to happen to someone. It's unlikely to be you, but if it happens to you, it was going to happen to someone. So, anyway, with the birthday problem, the question is always about how many pairs. How many actual pairs are available? It's not a matter of me asking the number of people, but rather how many people can ask each other. So if we have 6 people, there are 21 pairs you can make. It's a lot more questions than just 6 questions. Now, it's still pretty unlikely that if I have a group of 7 people, 6 people and myself, that there'll be a common birthday. Unless we weaken it. It's a fun fact that if you have 7 people, the odds are 50-50 that there's a birthday within a week of each other. But in any event, it's more likely to happen. Right? Moving back to DNA, I'm going to probably do a part 2 of this video. I'm running out of time. What are the odds of somebody matching me at 6 loci? Well, it's the probability of any 1 loci raised to the 6th power. So you work through it. It's about 1 in 5 million. Seems extraordinarily unlikely. Even more unlikely when you consider 9 loci. The odds are about 1 in 10 billion. So it seems like you would need 10 billion people to have a match. Think about these numbers. I'm going to pause this video and make a part 2.